Now the third canonical graph that we are going to see here, it's the structure that is shown in this figure over here, where we say that this is a head-to-head structure. Head-to-head structure, where we can see that the node of C, which represents the random variable C, has two arrows pointing towards it. And this is why we call it the head-to-head structure. And the joint distribution corresponding to this graph is given as this factorization over here, where you can see that it's a prior of PA and P of B multiplied by the conditional probability of C conditioned upon A and B over here. And in the case where if none of the random variables are observed, then marginalizing over both sides, we obtain the independence of A and B. So this is different from the previous two cases where A and B are generally not independent when we do not observe C. But in this case, when we do not observe C, A and B are inherently independent. We can prove this by doing this by computing the joint probability of A and B. We do this by marginalizing over C. Here's the joint probability distribution given by the graphical model here. So we can see that the probability of A and B here are independent of C, and we can pull it out of the summation sign. And this is a conditional probability of C, which we can marginalize over C. And hence this becomes, the sum of C over here becomes 1. Hence this marginalization resulted in probability of A multiplied by probability of B, which means that when we do not observe C, A and B are conditionally independent. And in the case where we observe the random variable C over here, then the probability of A and B, or the random variable of A and B, are not independent. It becomes dependent on each other. We can prove this by writing this conditional probability of A and B conditional upon C, and we express it into this form using the conditional probability. And then we can see that evaluating this term by substituting the joint probability with the factorized form from the graphical model, it's not reducible in general, and we can see that this term over here is still dependent on C, A, and B, and hence we can say that A and B are not conditionally independent given C. So this is different from the case, the previous two cases where when we observe C, A and B becomes conditionally independent. As I mentioned earlier, that this is known as the head-to-head structure, or otherwise known as the V structure. When C is not observed, then we say that the path between A and B is blocked. And when C is observed, then we say that the path between A and B are not blocked. So this V-shaped structure can be extended in the case where C has a descendant of D, a direct descendant of a random variable D over here. When D is not observed, then we say that the path between A and B is blocked. And when D is observed over here, then what happens here is that there is a direct path from A towards D, because C here would form a head-to-tail structure, and when C is not observed, there is a path. It opens up a path from A all the way to D. But in this case here, D is observed. D is observed here. So this will also open up a path for rebounding back towards C. And since this is a tail-to-head structure and C is not observed, this means that this path will be opened up from D to B. Hence, there is a direct path from A to D towards B in this particular case over here. An intuitive interpretation of the head-to-head structure will be given by the example over here, where we use the random variable B to represent the battery, the random variable F to represent the fuel, as well as a random variable G to represent the electric fuel gauge. So in general, when we do not observe anything from the electric fuel gauge, an observation, a knowledge on the battery state would not tell us anything about the fuel level and vice versa. This implies the conditional independence of the battery and fuel when the gauge is not observed. But when we observe the electric fuel gauge, and this, knowing the battery is flat, would actually lowers our belief that the fuel level is empty. And in this case, we say that an observation of the electric fuel gauge couples or make B, the random variable B, the battery state, dependent on the fuel level. This is otherwise known as the explaining away effect. This means that we are explaining away the independence between the two random variables B and F, given that we have observed the random variable G in the head-to-head structure. And in the case where there is an alarm that goes off when the fuel gauge is empty, if we observe that the alarm is going off right now, knowing that the battery is flat lowers our belief that the fuel tank is empty. And this means that the battery and the fuel status are no longer independent once we have observed the alarm. Here's a numerical example to further illustrate the conditional independence of the head-to-head structure. Let us denote the battery state as the random variable B. It could be either charged or flat. Let us further denote the random variable F to represent the fuel state, that is either full or empty, and G to be the electric gauge state, which either indicates that it's full or empty. Here we are given the marginal probability or the prior probability of B equals to 1. That means that the battery is full, equals to 0.9. What this means is that we always tend to have a high confidence that the battery in the car is fully charged, and the probability of F equals to 1 equals to 0.9. We are equally highly confident that the fuel tank is always full. And here we are also given the conditional probability of the electric fuel gauge, the indication of the electric fuel gauge, that is equals to 1. That means that it's indicating that the fuel tank is full. Condition upon the battery is full and the fuel tank is really full, it's 0.8. Notice that this is a conditional probability. What this means is that when the conditions are in the same states, then the sum of the probability of G should add up to 1. And an example here would be the probability of G equals to 0, condition upon B equals to 1, and F equals to 1. Since these are in the same states, it has to be 1 minus 0.8, and that's 0.2 over here. And we can compute the probability of P equals to G equals to 0, condition upon the respective states of B and F, by simply subtracting off one of all these values over here. Now suppose that we observe the fuel gauge and it reads empty, where that is G equals to 0. We have the probability, we want to compute the conditional probability that the fuel tank is really empty, conditioned upon the gauge is reading empty right now. And that would be given by using Bayes' rule. That would be given by this probability over here, where this is the likelihood of G equals to 0, condition upon F equals to 0, multiplied by the prior probability that the fuel tank is really empty, divided by the marginal probability of G equals to 0. Now let us first look at how to compute the denominator of the marginal probability of G equals to 0. We can simply do this by since this is the marginal probability of G, what it means is that I would have to marginalize off B and F from the joint probability distribution of B, F, and G. And this can be rewritten as the marginal probability marginalization of over B and F, and replacing this joint probability distribution here with our factorized probability from the graphical model, which is this conditional probability multiplied by the marginal probability of F and B over here. And since we are interested in computing the probability of G equals to 0, we can rewrite this into this form over here, sum over B, sum over F, and the probability of G equals to 0, B and F, and probability of B and probability of F. So what this means is that we have to compute the sum over all the combinations of B and F, where B and F equals to 0 in the state of 0, 1 respectively. And this means that we have to do the sum over 4 different times when B and F equals to 0, 0, 0, 1, 1, 0, and 1, 1. We can evaluate this sum into 4 different summation terms over here. So G0, B equals to 0, F equals to 0, multiplied by PB equals to 0, PF equals to 0, plus probability of G equals to 0 conditional upon B equals to 0, E equals F equals to 1, PB equals to 0, PF equals to 1, plus PG equals to 0 conditional upon PB equals to 1, F equals to 0, PB equals to 1, and PF equals to 0, plus the last probability term would be PG equals to 0 conditional upon PB equals to 1, F equals to 1, PB equals to 1, and PF equals to 1, where we can see that all these terms over here can be directly read off the tables that is given to us previously, and we can compute the marginal probability of PG equals to 0. And the next thing that we need to compute would be this term in the numerator, and this is given by the conditional probability of G conditional upon F can be rewritten as the joint probability of G and F divided by the marginal probability of F, and that can be rewritten as the marginalization over, since B here is not found in this numerator term, we will have to marginalize over B over the joint probability distribution of B, G, and F divided by the probability of F. And this term here can be rewritten as the marginalization over B following the graphical model, G conditional upon B, F multiplied by the prior probability of B and prior probability of F divided by the probability of F. So these two terms here can cancel off, and now we are left with this marginalization term over G conditional upon B, F multiplied by probability of B, which is given by here. So I'll leave it to you to evaluate this summation term, the marginalization term, which you can simply compute by following the standard rule that I have shown several times earlier in the lecture. Now, after computing the conditional probability, we can see that observing that the gauge reads empty, it makes it more likely that the tank is really empty, as we would intuitively expect, and as shown by this inequality of the probability distribution over here, of the probabilities over here. And if we also check the state of the battery and find that it's also flat, that is, that the state of B is equals to 0, we have now observed both the states of the fuel gauge and the battery. Let's compute a probability of the fuel being empty conditioned upon the gauge reads empty and the battery is flat. And this is given by, this can be easily computed using the Bayes rule. So here we simply flip this guy around and then divided by the marginal probability. I'll leave it to you to evaluate this term over here, and then following the steps of the computation, we can see that the probability, the conditional probability here equals to 0.111. So what happens here is that we can see that having observed that the electric gauge reads empty and the battery is flat right now, it actually tells us that our belief that the fuel tank is really empty actually drops when we saw that the battery state is 0, that the battery is indeed flat. What this means is that having observed the electric gauge reading, it makes the two random variables of battery and fuel coupled together. They are no longer independent of each other, and hence knowing the state of the battery would explain away the observation that the fuel gauge reads empty. So we have seen earlier in the d-separation principle of the three canonical graphs that A is conditionally independent of B given that we have observed C if all paths from A are blocked from the nodes in the set of B when all the nodes from set of C are observed. And we say that A is d-separated from B by C. And the joint distribution over all the variables in the graph will satisfy this conditional independence over here. So what it means here is that A, as what we have shown earlier, that A, B, and C is just one single random variable respectively, but it need not necessarily be so. So A can be a set of random variables, it can be a set of random variables, B can also be a set of random variables, and C can also be a set of random variables. And what it means is that once we observe the set of random variable C here, if it blocks the path from all the random variables in set A and it blocks all the set of random variables from A to B, then we say that the set of random variable A and is conditionally, then we say that the set of random variables in A is conditionally independent of B given the set of random variable in C. So from the three canonical three-node graphs, we say that any paths from A to B is blocked or d-separated if C forms a tail-to-tail or a head-to-tail structure with the set of A and B. This is the illustration over here, the graphical model over here of a head-to-tail structure where this is set A, this is set C, and this is set B. And in the second case over here is tail-to-tail where this is A, this is C, and this is B. We say that A and B are d-separated or blocked when C is observed in the first scenario over here. And in the second case here, we say that A and B are conditionally independent of each other when we do not observe the set of C. When A, B, and C forms a head-to-head structure, this means that it's given by this structure over here, the V-shaped structure, where this is A, B, and C. When C is not observed, then all the random variables in the set of A and B are conditionally independent of each other. The use of the d-separation principle to find all conditional independences in a Bayesian network can be summarized in the baseball algorithm. This is a reachability, otherwise known as the reachability algorithm, will shade the nodes in set C. This means that set C are all the observed nodes that we condition on, and we'll place a ball at each node in the set A, and then let the ball bounce around the graph according to the d-separation principle. If none of the balls reach B, set B, then A is conditionally independent of B given C, else it is not conditionally independent. And we can see that this algorithm can be implemented as a breadth-first search algorithm. So here's an example. We'll take the set of C to include the random variable x2 and x3. We'll first shade x2 and x3 where we condition upon, and for any random variable that is in the set of A, suppose that we are looking at set of A equals to x1 over here, we'll see that we'll start by passing a baseball from x1, and we try to do a breadth-first search. So here a baseball, we'll do a breadth search. Breadth search means that we are going to search level by level. Okay, this is the first level from x1, and here is also the first level from x1. We'll see that this ball over here is going to meet x2 and x3 at a head-to-tail structure. Head-to-tail structure in both cases. And since x2 and x3 are observed, this means that x1 is blocked from the rest of the random variables in this particular graph. And we can conclude that x1 is conditionally independent of x6 given x2 and x3. In fact, we can also conclude that x1 is conditionally independent of x4, x5, x6 given x2 and x3 over here. Now, another example over here would be, let's take the set of C to include x1 and x6 over here. Hence, we shade x1 and x6 over here. If we consider x2 to be in the set of A, then we can see that by using the breadth first search, we can pass a baseball towards 3 different directions over here. And in the case where the baseball is passed towards the direction of x1, we will meet up with a tail-to-tail structure where x1 is observed over here and the baseball will be blocked in this direction over here. Hence, it cannot roll over to x3 and x5 over here. And in the case of passing the baseball towards x4, of course, there is a direct link from x4 to x2. Hence, this x4 and x2, they are not conditionally independent. But when we look at this case over here, where we pass the baseball from x2 towards x6, and this is a unique structure of the head-to-head structure or the V-shaped structure, we can see that since x6 is observed, this makes x2 and x5 dependent on each other, which means that there is a path for us to roll the ball from x2 to x6 and towards x5. And hence, observing x6 and x1 doesn't mean that x2 is conditionally independent on x3 and x5. The last example that we are going to look at is the naive Bayes classifier. So here's the example where we want to classify emails as either a spam, which is denoted by y equals to 1, or not a spam, where y takes a state of 0. So y is the random variable. It's a binary random variable that either takes 0 or 1. And let 1 to n index the words in our vocabulary. Example, we have n number of words in English, for example. And then xn equals to 0 or 1, which is the binary random variable, which denotes the nth word appearing in an email or otherwise. So this means that I have n number of words, and suppose that the first word is the second word is he, the third word is she, and so on and so forth. So I have n number of these words over here. So each one of these words would be represented by a random variable x1, x2, x3, all the way to xn. And in the case where x1 equals to 1, this means that there appears in the email. And in the case where x1 equals to 0, this means that there doesn't appear in the email at all. And the emails are drawn according to some joint probability distribution, where it's a probability distribution of all the words and whether the email is a spam or not a spam. So we can see that what we can observe over here are all the words over here, and the individual words that that forms the vocabulary that we defined earlier. And this is conditioned, each one of the words is conditioned upon whether the email is a spam or not. And we can actually write this into a graphical model, represent this into a graphical model in this form or structure. So here we introduce another notation, which we call the plated notation, because notice that this arrow here is repeated n number of times over x1 to xn. So we can simply write this as y pointing to xn, small n, and a plated notation around it. N here meaning that this xn is replicated n number of times. So we'll first write the joint distribution using the chain rule over here into this form, where we bring y, where we condition upon y and multiply by the prior of y over here, which can be read off from this plated notation over here. Then since that we can further observe that every single random variable here given by this graphical model, the naive Bayes classifier graphical model over here, where if we observe y, condition upon y over here, if we observe y over here, then all the individual x1 to xn over here, they are independent of each other, because we can see that this is a tail-to-tail structure where passing a baseball from x1 will not be able to reach any other x over here. And similarly, for any other random variable x, we cannot pass a baseball to the other x in the graphical model. And hence, we can write this term over here, the joint probability or the conditional probability here, to be conditionally independent given y. And we can write it in a more elegant way by doing a product of the marginal probability or the conditional probability of the respective x random variable over here. Now once we have obtained the joint distribution according to the graphical model over here, we can predict with the Bayes rule on whether this email is a spam or not, given that we observe all the words that is in the email. And here we can do a Bayes rule to flip this around by saying that this is the likelihood of x conditioned upon y equals to 1 multiplied by the prior probability of y equals to 1 and divided by the normalizing constant over here. And we can actually determine the probability of whether this email is a spam or not. And the final concept that we want to look at is the concept of Markov Blanket. Formally, the Markov Blanket is defined as the set of parents, children, and co-parents of a node denoted by xi in this figure over here. So in this case here, given this particular node xi, we have the set of parents, all the parents over here. This is part of the Markov Blanket, and its children, all the children of this node over here, they are all Markov Blankets. And the co-parents of the children, so any co-parents here, if this is the case here, the co-parents of this guy here, they are all going to be in the Markov Blanket. And we will see that xi is conditionally independent of any other random variable in the whole graphical model, given that we have observed the Markov Blanket, all the random variables in the Markov Blanket. So here's a proof on the conditional independence. So suppose that I have xi conditioned upon all the random variables. So this includes the whole set of random variables in the graphical model. So this could be the whole graphical model that is in the set. And now I'm going to represent the conditional probability of xi conditioned upon all the random variables, all the other random variables except for xi itself. And this can be further evaluated using the chain rule over here. We can rewrite this as a division of the joint probability divided by the marginal probability over xi. And now we can rewrite this term into a product of the parent-child relation, as can be read off from the graphical model. This is what we learned earlier. And similarly, the joint probability in the denominator term can be replaced by these conditional probability terms over here. Then what we are going to do next is that we are going to factorize this into the factors that contains xi and not contain xi. So in the first term over here, we're going to directly write xi condition upon the parents. So this is the parent relation, the parent-child relation, where the parents of xi is the one that we want to condition upon. And in this case over here, the second term over here, it would be xm conditional upon all the parents of xm, where xi is in the parents of xm. So what this means is that we are looking at the relation of the children and the co-parents of xi. So because xi here is going to be in the parent, so here the xm here represents all the children. Xm here represents all the children of xi, and x pi of m over here, it would be all the parents of xm. So these are xm over here. So these guys here are all going to be the parents of xm, and where we denote that such that xi is in the set of x pi m, in the parents of xm over here, which is true in this case over here. And these terms over here, xl conditioned upon the parents of xl, they are all going to be any other nodes except for the parents, co-parents, and the children and xi itself. So we can see that these two terms over here, it appears twice in the numerator and the denominator. Since we are integrating over xi, which is independent of this term over here, we can pull this out of the integral sign, and these two terms here cancels out. So what we are left with over here would be the conditional probability of xi conditioned upon all the rest of the nodes in the graphical model, except for xi itself, is only dependent on the xi itself and its parent, its directly parents, plus all its co-parents and children. Hence, we can say that the co-parents, children, and the parents of xi forms the Markov blanket of xi. Here's the final step where we remove away the common term, and in this case here we can also see graphically in the graphical model that this is going to be true, because in this case where these two nodes here are the parents of xi, there are two cases where it can happen here, where there is this parent is linked to a node in a head to tail structure. So since this parent over here is observed, then the baseball over here from this node is blocked to the path of xi. Hence, these two are conditionally independent given the parents. So in the other case, it could be this direction pointing out this direction. And in this particular case here, we can see that this is a tail-to-tail structure. So having observed this random variable over here, we can see that the path from this random variable to xi is blocked. And in the case where this is that we observe the children, node over here, we can see that if we were to give a node over here in this particular structure over here, this forms a tail to head structure. And since this child over here is observed, that means that there is no direct path from xi to this node over here. And in the second case, where this guy here is pointing towards this structure over here, then this forms the head-to-head structure. And in this case, if this is observed, then this must also be observed as well, since this node over here in the head-to-head structure will form the co-parent of xi, and this must be within the Markov blanket. Hence, graphically, we also prove that given the Markov blanket, xi would be conditionally independent to all the rest of the nodes in the graphical model. Here's a real example of the use of Bayesian network. So I won't talk about the detail of the paper, but I hope that at this point of time, given the graphical model here, you would be able to write down the conditional probability distribution that can be factorized into this form over here. So what this graphical model simply means is that having observed some properties from the images, such as scene flow, occupancy, grid map, which represents the grid map of the scene, as well as scene labels. That means that each scene I want to label it, whether it belongs to a building, the road, and so on and so forth, or whether the vanishing point. So in this case, in this case, I would be able to observe some vanishing points. For example, this is going to converge at this particular point over here. These parallel lines are converging at this point over here, and by observing all these random variables over here, which I can see from the images that is given to me, or compute from the images as evidence. So I want to infer the road parameters. For example, how many lanes are there in the road, whether this is a T junction or a Y junction, etc. And I should be able to influence this by making use of the graphical model or Bayesian network. Here's another example that I've shown earlier in the introductory slide, that we actually make use of Bayesian network to model a robust 3D point cloud reconstruction. So suppose that I have fragments of the point cloud that look something like this, and the global poses of this point cloud is represented by Ti and Tj respectively, and I would have some observed constraints between the relative poses. So consecutive relative poses, I'll denote them as Xij, and which I also call the odometry constraint. And when the robot or the vehicle moves in a loop, for example, it will come back to a previously visited location. So these two fragments of the point cloud over here and here, they will form a non-consecutive fragments of constraint, which we call the loop closure constraint, denoted by the random variable Yij over here. So this random variable is also observed. These two random variables can be measured from our wave odometry sensor or the images, the LiDAR or the camera images sensors that's mounted here. And in the case of where there is a loop closure error, we will say that there is a possibility that this measurement over here, the loop closure constraint, the loop could be wrong. So we'll add an additional assignment variable, random variable here, to say whether this is correct or a wrong measurement. And if it is a wrong measurement, we want to disable it, or if it is a correct measurement, we want to enable it. And hence this can be formed as a graphical model here. And we make use, I'm not going to into the very detail of the technique, but we make use of the expectation maximization algorithm to solve this, because there's a parameter, unknown parameter, which is T over here, and as well as there is a latent set of random variable, which is the assignment random variable over here, that we need to solve it in an iterative step of expectation and maximization. So in summary, we have looked at the concepts of conditional independence, and we have seen how conditional independence can lead to a reduction in the computation complexity of a graphical model. And we explicitly use a Bayesian network to encode the conditional independence such that we can directly write them out into a factorized form of the joint distribution. We have also described the important concept of deseparation using the three canonical three-node graphs. And we have seen how to use the deseparation principle to deduce all the conditional independence in the Bayesian network using what we call the baseball algorithm. Finally, we have looked at the concepts of the Markov blanket. Thank you.